Well, hi, and you made it to yet another lesson, this one about the law of exponential change. The law of exponential change is something you are probably familiar with from your work in Algebra 2 or pre-calculus. But the teacher sort of said, well, it works this way because it works this way, now write it down. But in this course, we get to take a look at why it works that way and how they got the equation that they got. So that's what we're planning to do. Let me set things up for us. Let's suppose that for some quantity y, the derivative of y with respect to t is some constant times y. And let's suppose that there's some initial condition where that quantity y has some initial value when time is 0. And you've seen these questions in a bunch of different ways in your high school career. Some population where we know what the population is at a given time, and the population growth is what we would call exponential, meaning that the rate of growth, the dy dt, the rate of growth is proportional to the population itself. And that almost makes sense. The more people there are, the faster you can make people. That's sort of the way this goes. The rate of change is proportional to the quantity itself. Populations of bacteria, populations of people, sort of, a little. We'll get into why that's not entirely true. But anything like this, where the rate of change is proportional to the quantity itself. That's the topic of our lesson for the day. So let's use everything that we learned from last time. Let us separate, integrate, rah, rah, rah. If we separate, right, this has to come up, that has to go down. That's the mathematically legitimate way to do that. So we integrate. Antiderivative of 1 over y. Yes, you remember. I don't need absolute value brackets because we assume that the quantities in question are positive. Antiderivative of a number where t is the variable, right? Antiderivative of a number where t is the variable. Okay, and there's a plus c at the end for some reason. So I want y by itself. Well, if I want y by itself, I just exponentiate everything. And then I use a little bit of algebra. This is e to the kt times e to the c, right? We're adding exponents, so we're multiplying powers of the same base. But wait a second. This is an arbitrary number, and this is an actual number. So if I raise a number to a number, I get a number. Call it a. This is the thing they gave you in high school where they said, okay, the population is growing and it's growing according to this equation. And you asked, how did they know that it was growing according to this equation? Well, because the rate of change was proportional to the quantity itself, and this differential equation gets solved, and we get this as the law of exponential change. That is the law of exponential change. Okay? So what? Well, let's pretend. We'll just pull out the little red trolley and pretend. Let's pretend that bacteria grows in a way that is proportional to the number of bacteria. Well, this language is a dead giveaway for the law of exponential change. It's a dead giveaway. After 3 hours, there are 10,000 bacteria. After 5 hours, there are 40,000 bacteria. I want to know how many there are after 6 hours. Well, that's doable. That's very doable, in fact, because we know that the law of exponential change applies, and so we know that this equation applies. So after 3 hours, there are 10,000 bacteria. And after 5 hours, there are 40,000 bacteria. Right? So what am I going to do with those two equations? Let's divide. And if we divide, that's 4. The a's drop out. We get e to the 2k. So how do you solve? You take a natural log on both sides. And so k turns out to be half the natural log of 4, which happens to be the natural log of 2. Well, what do you do with that? Well, I want to know what's going on after 6 hours. Well, after 6 hours, we've got a e to the k t. Well, that's super, except we never figured out what a was. Well, let's figure out what a is. 10,000 bacteria is a times e to the 3 times ln of 2. And you can solve that and figure out that a is 1,250. And if you figure out that a is 1,250, then this a is 1,250, and y turns out to be 80,000 after 6 hours. So the question that I already hear you asking yourself is, do we have to show all that when the time comes? And the answer is no. As soon as I say, in a way that is proportional to the number of whatevers, that signals to you that it's the law of exponential change. And as soon as you have the law of exponential change, you have a scenario where we know this is the formula, go. Okay? Okay. Quick OYO for us. Let's talk about polonium-210. Polonium-210 decays according to the following. The amount of polonium there is equal to some initial amount called P sub 0, but this is really just a number, times e to the negative 0.005 t, where t is measured in days. I want to know a couple of things. I want to know the half-life of polonium-210 to the nearest day, and I want to know how long until 95% is gone. And if it's helpful to you, stick a number there, like 100 or whatever. The half-life is the time when half of this is left, and then figuring out when 95% is gone, well, that's easy too, if you make this a nice number like 100. It doesn't change how you do the problem. This is a calculator active question, and it should take you about 4 minutes. Okay? Okay. One more thing we should talk about. We should talk about Newton's law of cooling, named after that very famous mathematician, Cooling. Newton's law of cooling says that if you take the temperature of an object and subtract the temperature of its surroundings, let's say the room you're in is at 20 degrees Celsius, that's fairly standard room temperature, that would be the T sub S, the 20 degrees Celsius. That quantity is equal to the original temperature of the object minus the temperature of its surroundings times e to the minus kt. This is Newton's law of cooling. Now, I'm just going to throw in a side note here. Just a quick side note. This is the law of exponential change. This should look like this. And it kind of does. I mean, we've got some e to a constant times t. We've got e to a constant times t. This dash helps us know that if you put a pi on a counter, it will cool, not get warmer. The thing is, this A always signals an initial condition. Well, this signals an initial condition. This is the number of degrees different from the temperature of the surroundings. It's the net temperature, so to speak. And this is a quantity we're looking to track. Well, this is the quantity we're looking to track. How far that temperature is from the temperature of the surroundings. Because we know from Newton that if you leave the pi on the counter long enough, it will get to room temperature for all intents and purposes. Okay? So, let's pretend that apple pie comes out of the oven. And it comes out of the oven at 425 degrees. And it is placed on a 68-degree counter. 30 minutes later, it's 195 degrees. I want to know when. Is it 100 degrees? Because I think I could eat it right around then. Okay? So here's my thought. The difference between the temperature of the pie and the temperature of the room has to be this initial difference times e to the minus kt. And then there's an additional piece of information here that's going to help me figure out what k is. Right? That's going to help me know what k is. K is easy to find. It's some decimal number. It is some decimal number that you're going to want me to find, and I don't want to punch it into my calculator, but you're going to make me do that anyway, aren't you? Oh, golly. Okay. So 195 minus 68 is that number, divided by 357 is that number. So we've got 0.356. That's not actually it. There's a whole bunch of decimal places. Is e to the negative 30k. And so let's see, you take a natural log of that, and divide by minus 30, and you get that k is approximately 0.034452. We want to know when it's going to be 100 degrees Fahrenheit. Well, 100 minus 68 is 357 times e to the negative all that gobbledygook t, and that can be solved to find t. So 40 minutes after the pi is at 195, it's at 100. Okay, hopefully that's helpful to you. I think you will enjoy problems of this type, and I look forward to seeing you when we next gather. Thanks, everybody.